it's going to get complicated. Like it has been complicated already. Today, I want to show you the rest of the story, so to speak. Let's see, where do I find the stuff I want to show you? Let me go to examples. Here we go. So what I want to do is tell you a little bit about, hey, what's your name again?
Sagar.
Right, Sagar, right. So I want to tell you, so far we've been using as an example this thing I've been calling NAS. And hopefully, I don't know if I told you this, but it stands for Naval Air Station. And as you're well aware, you know, we're sitting right here on the island. The Naval Air Station's right over here, okay? And so if we blow up that part, it turns out that there's this outfall right over here, right at the edge of the seawall at the Naval Air Station. And so we had a project, and I wanted to know, is the outfall causing a problem in Corpus Christi Bay? And so that's why we actually went out and got this data. And so far, I have showed you, I think, data from only 1 month along one transect, okay? And we actually sampled 3 times, so there's dates, and we actually sampled more than just that one transect. So we use that word transect when we put stations on a line, and the lines can go in any direction. But this kind of, I guess we could call it half of a bullseye design, is real common in environmental pollution studies. So when you have a point source, right, you would expect any pollutants coming from the point source to disperse kind of evenly, right? And you would also expect that the dispersal of the pollutants will decrease with distance. In other words, there'll be a lot of pollutants close to the pipe, and as you move away from the pipe, the amount of pollutants should decrease until eventually you're in the background condition or reference condition. We never call this control. So what's the difference between a background, a reference, and a control?
Control would be the absence of anything, right? Or potentially, not necessarily.
Good, not necessarily.
Yeah.
Let's talk about that. So one thing is the total absence of something. So that would be either reference or background. Now, if it's, so control means you actually experimentally manipulated it somehow. You ran an experiment with and without something. When you do a field study, that's virtually impossible, right? Because you can't restart the world over back on January 1st and run it without the pipe. You can't go back to January 1st, run it with and without the pipe. We don't have time machines. We don't have that ability. So therefore, in field experiments, we call field work an experiment, we almost never use the word control. The only place where we might use the word control is, who works with Lee? You? You might use it once in a while. Imagine looking at the effect of predators on a community, and you set up some cages with and without the predators. Well, that's a real control. But what did you do? You controlled it. You actually made that manipulation. So when we do a field study like this, and we're comparing basically impact versus non-impact, that would be another way to describe these kinds of experiments. We never use the word control. Instead, we're going to use words like background and reference. So what's interviewing background and reference? Well, reference would be a place where you know it doesn't occur, but it's still exactly like the place where the impact you think is occurring. Now the problem with that is, it's just like you can't go back in time. There's this nasty scaling argument here. So how far away from here do we have to be for it to be exactly the same? The answer is usually you don't know. So you very seldom don't necessarily know what reference really represents. So reference is supposed to be without the effect, right? We sometimes are just never really going to know. So unless you have specific, I like to call it ancillary data, about, let's say, the concentration of the pollutants, you don't know whether you have a reference. So in a perfect world, you do these kind of studies in conjunction with chemists, and they measure the amount of pollutants in the water or the sediments, and you have stations with and without pollutants that are otherwise identical. And then you have a true reference. You don't have a control, but it's a reference. Now here's the nasty detail. They have to be alike except for the one thing. So let's think about this experiment for a minute, shall we? So we have this, so the pipe, this Corpus Christi Bay. Now what happens to depth as you move away from the shoreline? It increases. Are the sediments the same? No. How are the sediments different? Close to the shore and further away from the shore.
Finer, further away.
Bingo. You're going to get a little sandier, coarser. And why do we get sandier, coarser sediments on shorelines?
Watch out.
Because of waves. Because of energy. We call them high energy environments. And you've seen northers and how, we can actually get pretty serious pounding of waves along the shorelines. So the shoreline is going to be A, shallower, B, maybe sandier than offshore. So the problem is, and we expect the pollutants to just kind of spread out like that. Over here, we can have higher pollutants than here, maybe a little bit less than here, but is it still a true reference? No, it may not be at all, because other variables may be different. Depth may be different, sand may be different, the dissolved oxygen content may be different. For all we know, the availability of food is different. So now we start talking about background. So what really happens in a lot of these environmental studies is you're asking yourself, is my impact zone behaving differently from the non-impact zone in general? And the non-impact zone is equivalent to the word background. So something is going on in the natural world, right? Both with space and time, because those are our two major variables. But the scaling of that is different, and the number of confounding variables can increase. So typically what we do is we never actually ask ourselves, is near different from far? Typically we ask ourselves, is the near zone changing differently over space or time than the far or the background zone? That's what you're really asking yourself in an environmental study. And that is truly the definition of what we call an interaction. And when I say interaction right now, I'm using the statistical jargon sense. Interactions as a statistical jargon word. It means two variables are not behaving appropriately. So how do we find that out? Well, we find out, basically what I've also described is two different treatment levels, right? I said we have our spatial array of stations, right? So we characterize space with stations, different sampling locations, sites, areas, zones. Pick your favorite words. But never, ever, 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 ever use more than one word in a paper. Because no one's going to know what the difference is between a site and a station. And don't give me this crap like some of my grad students do that, well, I think it's boring to use the same word over and over again. No, it's called precise. It's called precision. So if in your first sentence you call it a station, don't start calling it sites later on, all right? Now, do we sometimes have sites and stations? Yes. In this particular design, we have this concept of a transect. Stations aligned along a transect, right? So we've got transects and stations, different words. In another sense, we might have near and far, right? These stations are the near sites. These stations are the far sites. There are multiple stations within a site. So you can use other words, don't get me wrong. Just use the damn words precisely, and don't ever, 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 ever create the unpardonable sin of the parallel construction, meaning you use one word to mean something different in different places. Once you define station, don't go off and start using other words or using it in a different context. Same thing with the word thing like site or zone or whatever you pick, okay? This is usually not, believe it or not only is this a problem with space, it's a problem with time. We run into things like months and seasons and weeks. And just yesterday, I was in a committee meeting, and we started asking ourselves, does it matter if samples are taken 2 weeks apart, 3 weeks apart, 7 weeks apart, 8 weeks apart? Can we call that the same time? Can we call that synoptic? How far away in time can two samples be taken and they're still considered synoptic? You know what synoptic means, right? You take it at the same time. Here's where I become a bit of a strict constructionist. And if they're not taken on the same damn day, I get worried. Forget about week. Once I go past 2 or 3 days, I start getting worried. These are not synoptic samples anymore. But do we do this? Yeah, in fact, when we look at this data set, you'll see it was impossible to sample 35 stations in one day. So the sampling actually occurred over a whole week. I actually don't remember. We'll look at the data in a minute. Which is a whole other problem, by the way. Suppose you have samples taken on different days, but you want to treat them as if they were synoptic. How the hell are we going to do that? There's programming tricks to deal with that issue as well. We'll show you those tricks today. So basically, we have these, it's pretty clear what we're trying to do here. Well, let me show you the next picture. So here's a little photo map of the exact sampling design. And hopefully you can see this. There are a bunch of little green dots we named, you see, we named the transects based on the degrees of the compass. And this one, as I recall, was about 270, or we called it shoreline, but it might be labeled as 270 in our data set. I don't even remember. But notice we've got some near stations, kind of 0 meters from, then some 10 meters, then some 100 meters. You see those orange dots? And the red dots way out there were 1,000 meters, 1,000, 1,000, 1,000, 1,000, okay? So we've got all of these stations, and we're gonna deal with the complexity of distance and radius down the road. For today, let's just say we have these, I think it's 35 stations, okay? So we got stations in time. So, uh-oh. Uh-oh. Does anybody have a pen? This happens to me every year. I forget to bring pens with me. I guess I'm still old school and I expect things like pens and chalk and erasers to be present in classrooms. But apparently that's not the rule anymore. I didn't get the memo that you gotta go buy your own stuff. Anyway, so what do we have here? So let's start building. What's the first thing you do when you're analyzing an experiment? What's our first step? What was the first thing we did with the one-way design? We built a picture. Let's build a picture of the design. So we've got these dates, 1, 2, 3, and we've got these stations, 1, 2, to 35. I'm not going to write 35 lines. I'm too lazy. 1, 2, out to 35. 1, 2, out to 35. And within each station, we have our 3 reps. Now we can do this. This is using the tree diagramming approach. We could also use a block diagram approach. We can do it like this, where we have date, 1, 2, 3. And we have stations, 1, 2, and then I'm going to skip to 35. Right, we can do it like that. For your homework assignments and project assignments, it's probably easier to use something like Excel to create a diagram like that. Right? So most people use it. And then what we can do is, instead of dots, we can fill each box with the number of samples. So we could use a tree diagramming approach. We could use a block diagramming approach to build a picture. But when we look at it, we see everything we need to see in a real important way, right? And the main point is, once we can look at it, we learn a whole bunch of things. One, we learn that there are 2 main treatments, right? Stations and dates. And the second thing we've learned is that it's a completely cross design, and we'll talk about cross versus nested later, okay? But for just now, we'll call it a cross design. Cross means every level of one treatment occurs within every level of the other treatment. I'll say it again. Cross means every level of one treatment occurs within every level of the other treatments. So the treatments are two treatments, right? Date and station. And date has 3 levels, and I could be wrong, but I think there are 35 stations. We'll check that out in a few minutes. I'm pretty sure it was 35 stations. So now, what's the next step? We've built our diagram. Based on our diagram, we're ready to construct a statistical model. Okay? That's step number 2. So what's our statistical model for? And there are 2 treatments, so we call this a two-way design, by the way. All right? So this is because there's 2 treatments, we call it a two-way design. When we had just stations, in our first example, we called it a one-way design because there was 1 treatment. So we build a statistical model. We have y is going to change, going to change as a function of the overall sample mean plus some thing called alpha sub j, where alpha stands for date and j ranges from 1 to 3, right? Plus beta sub k, where beta stands for stations, and there are 35, let's assume there are 35 stations. Now, here's the trick. And the trick is the interaction. So it turns out there's something about are things behaving the same way across from 1,1 to 2,2. And that's called the interaction. And that's modeled as alpha beta j sub k. And there should be 35 times 3 is 105 of those, right? So j sub k is going to go from 1 to 105, plus our error term. So you have i's within j sub k, and I is the number of reps, it's 3. So the data set should have a total of 3 times 105 when we get done. Now the other important thing I've just showed you is how to keep track, how the subscripts are so important that keep me track of every single friggin' row. And you should be able to recreate your design in your brain in seconds, just like I did, because you're simply multiplying your subscripts together. That's why the subscripts are so important. And when you're writing this, when you're writing it in your method statement, you're going to describe it all exactly the way I just described you. Describe it to you. You'll say, we have, one treatment, alpha sub j, where j equals 1 to 3 because there are 3 levels of alpha, and beta, which stands for stations in this case, and the k ranges from blah, 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 and then the interaction term. And you literally write words out exactly like that. And when you read my papers where I describe these designs, you'll see I actually write it exactly like I just said it. There's no reason on earth not to write it correctly. Now that's our statistical model. So that's our, written in math jargon, right? This is in math jargon. Now, the next step is, so let's go over the steps here, right? Draw a figure. Draw a stat model. Now we're up to step 3. What's step 3? Draw a SAS model. And when you leave my course, if you prefer to work with other software, I don't care. You do whatever you want to do for the rest of your life. It's just that depending on what software you choose, step 3 is different. That's the punchline. So how do we take, so what statistical software does, and all of it doesn't matter what your favorite brand of software is, all it's doing is it's implementing your statistical model so that you can calculate your probability values. That's really all you're doing. And as you might imagine, there are a lot of smart people in the world, and they all have slightly different ways of doing things, right? And there's nothing wrong with that. Diversity is great. So every single software package has this tendency to do it all slightly differently. So that's just part of the game. So now we're going to build SAS code. How do we build SAS code here? Well, y equals A, B, A star B, semicolon, and we're done. So in SAS always assumes that an intercept exists. This is our intercept, right? And it always assumes random error and replication exists. And that's where this comes from. If you have no replication, then I is 0. What is the value of this term? 0 times 3 times 35 equals?
0.
0, right? So you won't have any error if you don't have replication, which means by definition, you can never statistically analyze a data set with no replication. So I should never have to say anything more about that, right? Now what happens if, for one reason or another, you just can't get more replication? It's actually not a problem, because you know what we could do? We could actually use this as our error term. And then what we have is what's called a one-way block design. This is actually really common. It's most common with time series stuff. I do this all the time. So how many of you have used a sonde? You know what a sonde is? A water quality sonde? Well, you can moor it, and it can take data every 15 minutes for weeks. So now you have this enormous data set with, let's say, pick your favorite variables, salinity, dissolved oxygen, and you have a measurement every 15 minutes for, let's say, a week. And you have 2 sondes only, because they're like $10,000 a piece. And you put, so the question is, and you put one here, and one out there. Well, how do we know if the 2 sites are different? We have no replication. But we have those, we could use time as what's called a block. And we have this left over as our mean square error. So a one-way block design, and I'll show you how that would work here. We'll figure out which one we want to use as a block later. I'll illustrate a one-way block. We could use stations, for example. Let's say that the only thing we really cared about was change over time. We want to know if Corpus Christi Bay was changing over time. Well, we could use the stations as a block if we had no replication. And then, you know, time would be our treatment, and this would be the block, and essentially that would be our error term. But the model would look like this. Y equals mu, here's time, right? Plus B sub k. But there's no replication, right? So now our error term is simply J sub k. And we call this a block. And again, the word block is a statistical jargon term. What it means is there's no interactions. We're assuming that all the stations act exactly the same every time. In this model, that term tests that hypothesis. Are the stations changing the same way over time? That's an interaction. We assume a parallel response starting out. Because in fact, if it's not, that means we can't compare our stations. We're behaving one way, and stations over there are behaving a different way. that's a significant interaction. And it means our treatment level test is absolutely meaningless for both of those. We'll get into those details in a minute as well. Okay, so here's our two-way. And here is our one-way block. We got one treatment and one block. 1 plus 1 equals 2. So we have an alpha and a beta. And you do the SAS model pretty simply. Done. Done. What does this mean? This means this part is left over, and we can use that as our error term to test if there are treatment differences, the differences over time. And it means the beta test is meaningless. We don't care if it's different or not. We're just using it to explain variance in our problem. That's called statistical control. Again, that's a jargon term. Statistical control is where you account for variability that's outside of your physical control. You can't do an experiment to change those stations, right? But you know there may be geographical differences. So a form of statistical control, it's a lot like a form of replication. You just take a lot of them, and the variability amongst them we'll use to create our mean square error or our variance for your overall problem. In other words, we use that to estimate this term. So the whole goal here is always estimating your error term and using that to test if your treatments or levels are different. That's the whole purpose of all this stuff, going back to the early 1930s when this whole methodology was first invented by R.A. Fisher. So you've heard that name before? Okay. And we also like to call this the frequentist or empirical approach to statistics. As you may or may not be aware, hopefully we'll have time to get into this in detail at the end of the course. I always save this for last, because if I don't go through it, that's fine. This whole approach is under fire today by the so-called Bayesian people. There are a whole group of statisticians who think that this entire approach is pure bullshit. And it never should have been invented, and it's the most evil thing in the world. I think these people are silly. Okay? That's my personal point of view. And particularly when you understand exactly what they offer as an alternative, you really start scratching your head and saying to yourself, I don't get it. But like I said, I've got a whole lecture to prepare on Bayesian statistics, and if we have time, we'll get to those horrible, gory details later. Not that the Bayesian world is wrong, it's just that for the kind of things I do, it's not a better alternative at all. It's a lie that's a better alternative. Anyway, so what are we going to do next? Let's start implementing all this stuff, right? Let's do it. I need my glasses, I can't see my computer without it. So this little map is on the website, okay? And as you might imagine, we have a data set. It's called NAS MASP. If I can find it. NAS MASP. There it is. This data set is on the website. And guess what our first thing we have to do is? We got to import it. And notice, there's something missing here. So this is my metadata page. There are two important things missing from this metadata page, and I can't believe I've never noticed this before. I've been doing this for a long time. And I've got the maps here. So the metadata page, there are actually a lot of things missing from this data page. Well, what are the two most important things missing from this data page? What did you learn in like 3rd or 4th grade that goes on every
Put
single
your name
thing?
and your date.
Your name and your date. So let's fix this damn data page. I can't believe I don't have that. So what this really should say is, you know, you can put down source. Paul Montagna. And I can put my address, email, all this stuff like that. And I'm going to put date. And actually, I believe the date of this data set was created with something like, let's look. Well, it says 2016, that's not right. This looks more, let's use this date, September 2009. That's probably when I really created it. And of course, you know, you can update the date when you change the data set. And then this one is description. Naval Air Station macrofauna species data by replicate core. Samples taken to a depth of 10 centimeters, so we don't have to add the sections. Multiply by 28.36 to get number per meter squared. Samples, I hate the word taken. I can't believe I used that word. I should have said collected by Paul Krause, Scott Carr. I'm 99% sure that Rick Kolke actually did all this as well. Because I know I didn't do it. Who knows, maybe Rick didn't go on those cruises. I'll have to check. You know what, I bet he didn't go there. I bet his name would have been there if he had been. Let's not change that. And now here's a reference. So this is published data. And here's where I describe the experimental design with our treatments, our level numbers. Now, for right now, we're going to ignore this distance and radius stuff. We're going to just talk about stations. And in fact, that's the way it's described here, right? Now, variable names, this should say macrofauna sheet. Can't believe how lousy this is. And notice I have the variable name and the description. So we actually need another row right here, don't we? Where we have, we'll underline that. This is the variable name. And here's our description. So when you submit your data for your project, I want to see an Excel file, and I want to see it designed exactly like this. I want to see a metadata sheet, and then you might have just one sheet of data, or you might need more. But like all my data sets, there's actually 1, 2, 3 other sheets, because I basically use a relational style. These are technically all flat files, but we use a relational database style. It would only be a true relational database if I had one key variable up front to connect all the sheets. But I don't. For example, for station, right, that connects to here. It gives you the how station, see here's that variable called station. And the locations of those stations are here, okay? And then I have a variable called SP. And here's your SP code. That shouldn't say SP. That should, wait a minute. What does that say? What's that called? SP, right?
No.
What's that called? That's friggin' wrong. You can't match merge variables unless they have the same name. There are all kinds of errors in this thing. So here's the species name, okay? Here's the species code and the species name. And we can match merge those things together. And we're gonna get to that programming stuff pretty soon, actually. How these sheets come together to form one big database, okay? But this data set, what you've seen so far is probably just, you've seen that part of the data set so far, okay? You saw one day and one station and the 3 reps. So what we do now is expose all the stations and all the replicates. And as I said earlier, I believe that the station names, the first value is the direction, the second value is the distance from shore. So let's look at this real quick. This is 2-1. You know, I don't believe this. I'll bet if I go back and check that, I'll bet you anything that those samples were not all taken on the same day. I'm positive they were. Because I know it's, can you imagine taking 20, 35 samples in one day? How many stations can we get done in a day? If you really rocket it and they're close together.
And they're
10?
all together.
They're all
maybe,
maybe 10?
maybe 10.
12?
Maybe 10.
So, I gotta rebuild this data set with all the real values. It'll make it more fun. Anyway, so that's what the data set looks like. I'm gonna save it now. In fact, hopefully I'm gonna remember. What I'm gonna do is I'm actually gonna put this in Dropbox because it's a better, I'll change it later in Blackboard. Okay, so what's the first thing we do? Is we import. So, file, import data. It's in an Excel workbook. We'll browse for it. It's in, I actually have a shortcut over here to where it is. Oh, look, it's on top because I just saved it. NASB, and we go, okay. No, I don't want that data sheet. I want macrofauna. And we go lot, and I'm just going to call it M because I'm lazy. And notice I'm putting it directly in work. You don't have to do that. In fact, what we can do is I have a data set called ED, and we actually already have it here as something else, but we'll replace it. That's its actual name, so we'll call it that. So that's going to create a real data set. Here, import wizard can create a SAS file with all of these statements. You can either save it or not. This would be a good case again to save it so that you could use it over again for the other sheets. Or if your data set changes, it's a lot faster to submit code you already have than to click through all this crap over and over and over again. But I'm lazy, so I'm not going to do it right now. Yeah, let's go ahead and replace it. So now we have a data set called NASP. So the word NAS stands for Naval Air Station. MASP stands for macrofauna species, because that's what this is, macrofauna species data. So you can imagine me creating a bunch of other files for the other sheets. But when you do things like that, you probably want to stick them all in one folder, or you want to give them derivative names that all make sense. So I might have a file called NAS, just SP codes for the species codes. I might have one called NAS locations for the latitude and longitudes. But the trick I'm telling you right now is the way you name files really matters. You've noticed that when I do all this stuff, I've got hundreds, in many of my folders, thousands of files. This is what happens when you get old. You accumulate stuff over time. And you've got to carry that crap around with you for like the rest of your life. And if you don't give things good file names, two nasty things happen. One, you can never find it. And B, even when you're looking at file names, you have no idea what the hell's in it, because you can't remember. So a long time ago, when I say a long time ago, I mean like in the late 1980s, I finally figured this out. But it took me a good 10 or 15 years to figure this out. So what I always do is I give every file usually a 2 or 3 level name. And I didn't do it here, but I typically use an underscore in between file names. You could also use a period in between file names. So what I try and do is I make every file name a sentence, and I think in words. So my first word of every sentence is always the project or the experiment. So everything related to NAS, I would start with NAS, and then I would typically use an underscore. And then the second word would be the data type, like MA for macrofauna, HY for hydrographic data, maybe SAL for salinity data, maybe NAS Chem for chemical data. I think there's a whole chemical data set that goes with this. I know there is. You know, and blah, 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 blah. So, and then the third word might be either a version or more details about something. So what I'm telling you is, when you write file names, think in the context of sentences and parts of the name or words, and use the same exact good grammar, structure, and practices you would do with creating sentences, okay? That's my hint, my little gift to you. Which is why I ask you when you send me homework, what's the first word in your file name? Your last name, okay? That's always the first word. What's the second word? The assignment number. Well, if you need a third word, you might version it. Several of you have had to stick in version 1, version 2. If you don't use a version in your first one, that's no worries. You can add it in the second one. If you have to write over a file and you want to keep the original, just go, V2. And by default, you always know if you don't see a V, the other one was V1, all right? So those are the tricks on how to create useful file names so that in the future, it's easy, A, it's easy to find stuff, and B, when you read your file name, you'll actually understand what's there because you've written a sentence that makes sense. Now, one of the nice things about the Windows world today is I think we have 256 characters. So you could go crazy. I strongly recommend against that. So it's real interesting. My son is kind of a database manager for a software company. And his biggest problem is when people's file names are too long. And all of a sudden Windows can't tell the difference between 8 or 9 files because the first 256 characters are all the same. He runs into that problem all the time. So don't go crazy with length. Is my message. Don't overuse it. Now I don't know what the limit is for SAS file names. I'd actually have to go look it up again. But I've never bumped into it because mostly I'm lazy and I don't like to type a lot. So I have a tendency to keep my names pretty short. But you don't have to do that. Okay, that's just the way I do things. All right. So let's look at our file and see if this worked. So we should have something called NAS MASP. And it looks like it worked fine, right? Trust me, it looks exactly like my spreadsheet. But you should never trust it. My trick is I proofread the first line and the last line. I might pick one in the middle. But typically, if your first line is perfect and your last line is perfect, everything in between will be good, right, Evan?
Yeah.
There are other ways you could check this. Sometimes I have nasty data sets with missing values, with characters in the middle of a number field, and I don't trust it. Or there's something about the import that doesn't look right. The question is, how do I proofread? This is only 400 or 500 lines. Suppose I'm pulling in 10,000 lines. Am I really going to sit there and proofread every line? No. So what's a good trick? Particularly if you're concerned that this field might have got corrupted. You can go to Excel, you can sum the whole damn thing, and then sum it in SAS and see if you get the same number. We call that a checksum procedure. We could look for outliers. We can write, so you can do proc means, data set name, write your variable, and see if we get the same number in SAS and in Excel. Sounds like a good homework assignment. What's another way to do it? We could look for outliers in a data set. If n is less than 0, output. That will create a data set only of negative values. Hopefully that data set has got 0 lines in it, right? Because there are no negative values in this level. I also know that I can never get a number over, let's say, 300. So you can go to, again, you go to Excel, you do a quick sort, what's the biggest number? And then you come here and you ask it, if the biggest number is, let's say, 123, you write a data step, data, test, semicolon, set, the file name. If n is greater than 123, then output, run. That will create a new data set, but only if those outliers exist. So my point is, you've got 2 easy ways to run programs to check your data set without proofreading every friggin' line. You can use this checksum approach, which will only work, right? It's only going to work on numeric variables, which are right justified. Will it work here? No, that's a character. Will it work here? Believe it or not, yes, but there's a lot of little tricks, so you don't want to, might not be the best way to do it. But we can do something else, right? Let's make sure, how do we figure out if all of our date and station names are right? Well, why don't we pull out all the unique date and stations? And we'll have a list. And then we can check that list against the Excel list. And if they're all correct, then we know that it read all those characters and all those dates incorrectly. So what's the easiest way now to get a list of all the dates and stations? Which proc would we use? Hell, we can use proc sort. It's actually probably easiest. We could also, proc print would give us the whole data set. That would be a terrible way to do it. But proc summary would do it as well. So let's do that real quick. So let's imagine something like proc sort data equals ed dot nas nasp. Now I'm going to go out equals. Why am I doing out equals? I don't want to write over my data set. Sort replaces your data set. I almost never use proc sort without the out statement. No, I can say this. If it's a permanent file with a two-level name, I never use sort without an out statement. I only use it without the out statement when it's a work file, because I know I'm throwing that file away when I'm done anyway. So we'll call this, I might have, let's go look at my work directory. I think it's empty. Nothing there. Let's call it M. And then we're going to say no dupe key. So that'll give us each name only once. And then we'll go by date station, run, and then we can do a proc print data equals M, and I'm only going to print those variables, date, station, run. So I'm going to reduce that. Let's go here, let's run it. And so this is those interactions of every date and station. Well, wait a minute. Station 00 occurs here and here. That's not what I want. I wanted one for dates, one for stations. So let's change that program. And hell, since this is going to be just dates, let's call it D for dates. And then let's go here and copy it, paste it, and we'll change this one to S for stations. So this is going to be S over here, movie station. Now let's run it. Oh, that's what I wanted. So here are all my station names, and there are only 15 of them. Oh, I lied. There are only 15 stations. Yeah, maybe you could get 15 done in a day. It'd be a long day. And if we go up, oh, look at that. Look at that. How come there's more than one date? Something went wrong. Let's look at that data set. Ah, I see. I printed the wrong data set. Ah! Let's print the right data set. Okay, and then there are 3 dates. And they all look right. And I can compare this sheet to the metadata sheet, and I got it made. In fact, how else could this be useful? You could use these approaches. I can cut and paste these tables into Excel. I can create my metadata this way. So if you have a raw data set, you could actually create metadata using these approaches as well. All right. Now, let's go back and look at, so what we have here is, we only have one section, so we don't have to add them together. But if we want to analyze our two-way ANOVA data for things like total, abundance, and number of species, which is the 4th step in our hit parade. We've got to put our data in an analyzable format. And I've said this many times before, I'll say it again. I can guarantee you, you will never open a data file and it's analyzable right off the get-go, unless it's super simple. You're always going to have to do something to it to make it analyzable. Okay? So, what do we have to do to this particular data set? In each sample, we have the count for every species. So here's replicate 1, which is sample 1 for this date and station. We have how many species? 1, 2. The total number is 1 plus 6. So what we want is date station rep with the total count and the total number of species. And how do we get that? How do we get that? Well, we use proc means and the sum. The easiest way to get it is with proc means. So let's do that. I'm going to copy this. So let me put some titles up here. So we'll call this Title 1. Using sort with do key to list treatment levels. Okay? That's the first thing we did. The next thing we're going to do is, tell you what, we need this whole thing. I'm going to copy all that, copy. The next thing we're going to do is, and we'll replace that title. And I'm going to go quote, quote, semicolon, and back up, because I never trust myself to leave a text string, complete. So we're going to create a composite data set. And so we're going to use proc means, so the first thing we're going to do is sort. We'll call it out equals, we'll use end. Obviously we don't want no do key. Now what are the variables? We're going to go date, station, rep. We can ignore section, SP. And then we're going to use our proc means. Data equals M. And we got to write no print, remember? Because by default it creates an output. We don't want an output here. So what variables should we do? Let's use both count and M2. So I'm going to go N for count, and M2 for number per meter squared. And now we want to create a data set. We do that with, I always like to indent these things. Whoops. Just so I can see what parts, which statements go with which procs. Out, put, out equals, and I'm just going to call this S for sums. And we'll use the sum function. And we're going to use both N and M and 2. So let's see what that does. Whoops. What did I forget? I forgot my date station thing. Copy. Because I got the overall mean. So I want this all done by date station rep, so that's where I stop my by statement here. One more time of feeling. So let's open up N. Now, we'll check the first replicate on, the first date station combination only. So this should be 2 and 7. And, whoops, that's the wrong data set. S. So the first one should be 2 in the frequency column, and it should be 7, that's correct. The next one has 1, 2, 3, 4, 5, and it adds up to 4, 18, 19, 20, 21, and that's correct. And the third one is 3, and that's correct. And those 3 add up to 8 plus 10 is 18, plus 1 is 19, and that's correct. So now we have our composite data set, but it's ugly, right? So now let's make it pretty. And the pretty one, I don't want to have to do this over and over and over again. So I'm going to go ahead and keep it. Data, ed.nas. I'm going to call this one NAS2. We call the one-way design NAS1, so what the hell, I'm going to call this NAS2. We can call it anything we want to, really. And we're going to use, so the set statement tells us which one we're going to use. We're going to use S. And the first thing we want to do is get rid of the crap. We're going to drop type and frequency. But we actually want to create a new variable called, do we want to use S or R for richness?
We're going to use S.
You like S? We'll use S. S equals the frequency, right? You see, it doesn't matter where the drop statement happens. In some programming languages, if you put the drop first, frequency would not be available. You would have to put drop last. But in SAS, it doesn't matter where drop gets put. SAS is kind of funny. It reads all of your programming statements, and then it decides what order it's going to execute them in. Then it executes them in its own little unique way. And it'll automatically put things like drop last. So you don't have to worry about where you put the order of these things. That's not true in most programming languages, by the way. Order matters. You can write your program perfectly, but if they're not in the perfect order, you won't get the same result. Now, what else do we want to do? Why don't we create you know, I really don't like, let's see, all of these were in, since all these are the same dates, since all these are the same dates, I don't really need to see 1 February 94, right? We could just format that date so that all we see is the month name. So let's format date as month name, month, M-A-N-E, 3. Okay? And so that will make this just look like the word February. Now, 1994 and the actual date will still be there. What the format statement does is it just shows how it's displayed. And, you know, these big abundances here, I don't know about you, but numbers like 11,000, I like to see in a comma format. So NM2, we're going to go comma 8.0. So that says, give me 8 places. So the comma takes one, so I could, the biggest number I could have would be 99,000, which is enough. If I have numbers like 100,000, I'm going to need a bigger format. And the 0 means round it off to the nearest whole number. And what else do we want to do to this data set? Should we go ahead and create our log transforms now? Yeah, what the hell. So let's have a variable called L, number per meter squared. And that equals log, number per meter squared, plus 1. And let's have let's log transform S. LS equals log, S plus 1. Now, I'm going to run that just so you see the differences. Then we're going to do some more. Unfortunately, I've got to go back here because I save this as permanent. So NAS2 now looks like this. And you can see it looks exactly like S. We've converted frequency into our new column called S, right? And we've added log, and look at how the dates look. This says February. What other date formats are there? Well, we could have had Feb 94 by using MONYY. We could have Feb 19. So if we do other date formats are MONYY. If we go 5, then we would have Feb 94. If we go 7, we'd have Feb 1994. Okay? So we have lots of date formats. If you don't like this, let's say you're a person who would like to see that as 2/1/94. Well, that's MMDDYY. Bottom line is there must be 30 or 40 different date formats, and you can make the date look any way you want it to look. Okay? Now, I also have my log transform values right there. So we're in good shape. So let's look at this data set carefully and make sure everything is correct. Oh, I see an error already. Look at this. When there are no species, when there's nothing in a sample, it says there's one species. Why the hell is that happening? Well, recall that we have a placeholder called nothing found. I think my species code for that is 999. If we find nothing in the sample, it's actually 0. I have to keep track that the sample was taken so that we know there's a third web, and eventually we divide by 3 to get the correct mean. Right? The mean of 1 and 1 is not going to be, the mean of 2, 1, and 0 is not going to be 1, right? If you divide by 2. So only be 1, we divide by 3. So we got to tell it, look, don't count, don't tell me there's a species there. Don't tell me there's a species there if there's nothing there. So what are we going to use here? Oops, I'm way over time. So I'll just do this and we'll quit. There's actually more I need to do. We'll close that. So we're going to add another line that says if S equals 0, whoops, if N equals 0, then S equals 0. Okay, that'll fix it. So I'm going to do a whole bunch of other stuff, but I'll prove to you that fixes it.
You typed D instead of then.
What?
Did if D instead of if then.
If N equals 0, then. Let's see if it worked. Oh, look, SAS knew what I was trying to do, so it already did it correctly. Yeah, it worked anyway. Look, see it? All right, so I'm going to quit today. We'll save everything we've done so far, and we'll pick up. We're going to do more to this on Thursday. But I'm already 5 minutes over, so go ahead and run if you got to run. So I'll go ahead and save this to my Dropbox right now. But before I save it, let's give it a good name. So one of the things I like to do with all my programs is I like to put a comment field with the program name and the description. Okay, so we'll call this NAS2.SAS, and our description is this program creates a composite data set from NASP. Okay? So we'll just call it NAS2.SAS. Save as. And we're going to put it in Dropbox. Oh good, I have my shortcut right there. And you'll see I've renamed all of these files so they all make sense, hopefully. So we're going to call this one NAS2 composite. And what's the next step? After we create our data set, we're going to explore, analyze, interrogate, and visualize. So we're going to do all these steps next. Well, hopefully we'll finish all that by Friday for the 2 exams. All right, like I said, you all need to run. I've taken way too much time. I get carried away.